Okay, so I'm walking around and I'm seeing some people getting a really good start on this, and I'm seeing a few people that look like they're a little stumped. So I'm going to give you kind of the start of this question, a little tip to see if I can push you not off the cliff, but like towards the right answer. Okay. So what we have is a question where we have a projectile that is projected horizontally. Okay, a person who runs off of a cliff is running horizontally at the beginning of the question. All right. So we have this situation here. Right. We are looking for, okay, how tall the cliff is going to be. So we don't know this, the height of the cliff, but we do know that they're moving at 8 meters per second horizontally, and that they hit the water 15 meters from the base of the cliff. Right. What else do we know?
Acceleration.
We know the acceleration is 9.81 meters per second squared. What else? Nope, we don't know the final velocity. I know you're thinking it should be 0, but that would be after they hit the water, right? They would decelerate through the water. So we don't know for sure that it actually isn't 0, because we're looking for the instant they hit the water. Okay, so here's what we have to remember. Any projectile motion problem, whether it's projected horizontally or projected at an angle, needs to be divided up into its vertical component, which undergoes accelerated motion, and its horizontal component that undergoes constant velocity. So from a horizontal perspective, we know how fast the person was running, and we know how far they traveled. From a vertical perspective, we know the acceleration, and we also know the initial vertical velocity. How fast are they going vertically when they run off the cliff?
0.
0. Okay, the question wants me to find the vertical distance traveled. Okay, that's the height of the cliff. I need one more piece of information to get that. Okay, probably see if you got a way to find that. Maybe using the horizontal information. Okay, because the whole time the person's moving horizontally, they're also falling. So the time is the one thing that is shared by both vertical and horizontal components. All right, give you a couple more minutes, see how you do there. Okay, let's have a look at the rest of this. So, since we know that horizontally the object travels at a constant speed, we can be sure that this formula would apply to that movement. V equals d over t. And I have both d and v. So I can solve for the time of the fall. Right? So time will equal d over v. So that'll be 15 over 8. Right? Which can be like, what, 1.8 or something? 1.875? Okay. So 1.875 is my time, 1.875 seconds. The whole time they're traveling horizontally, they're also falling. So that time can come over here. It's the one variable that applies to both. Okay? All right, now that I have time, do I have enough information vertically to solve for d? Yeah. And I can use this formula here. D equals vi times t plus 1/2 at squared. And I can simplify it because vi is 0. Right? I just have to go 1/2 at squared, and I'll have the distance traveled. Okay, so 1/2 times 9.81. And I'm not making that negative because everything is down in this question. I could make it negative if I wanted, but then I'll get a negative displacement, which is down. Okay, times 1.875 squared. Right, so 0.5 times 9.81 times 1.875 squared. Okay, so we're looking at a fall of 17.2 meters. Okay, so the cliff to two significant figures would be 17 meters. Okay. Did I make it actually 8? Okay. E equals 2 times 10 to the 1 meters. Good catch. I would never give you a question that was not significant. I just think that's it. All right. Questions on that? Yeah, so that's what horizontally projected projectile motion problems look like. Okay? Either you're going to be asked to solve for the height of the cliff, or you're going to be asked to solve for how far the person hits from the base of the cliff. Once in a while, you might be asked to calculate how fast they ran off the cliff at. Okay? There's really only about 3 things you'd be asked to solve for. They all require you to know the time. Okay? Basically, all projectile motion questions, time is the most important variable because it's the only one that applies to both horizontal and vertical components. Okay? All right. Now, I want to talk to you about projectiles projected at an angle. Okay? So, I told you yesterday I was going to show you this video of the Mega Whoosh water slide. Okay? Something like that. Okay? So, these guys in Europe, they build this giant slip and slide. Okay, so you know, like the yellow kind of plasticky thing that you slide down. They put this on this like huge hill, and they build this ramp out of wood. Okay, and they run the slip and slide up onto the ramp. So the guy comes sliding down this hill, going super fast, and he flies off of this jump. And he flies through the air, like a crazy distance, and lands in one of those little blue inflatable kiddie pools. Okay, you know the ones, like they're literally no more than about 6 feet across and 3 feet deep. Okay, right? There's no way that a guy survives landing in that pool. Like, that's not a life-saving amount of water. Okay, you would still bottom out on that pool, probably break the pool, okay, and die, or be horribly injured. Okay, but in the video, it looks terribly impressive and really realistic, given when it was made. Okay, it was quite a long time ago. So I'm going to show you that video, and then we'll look at the question itself, and then we'll watch Adam and Jamie bust it. Yes, because they actually did, which is pretty cool. So let's say this is the slide that we just watched, right? So he's going to come flying down here, and he's going to go off that ramp at 20 meters per second at an angle of 30 degrees. What we want to figure out is how far away does the pool have to be for him to safely land in? Because this is the math they would have had to have done in order to have actually pulled this off, which they didn't. But we're going to say that they did. All right? So what we have here is our initial projectile triangle. Okay? Very much like what we learned about in the vector addition stuff. Okay? The hypotenuse of the triangle is what we call the projected velocity. It's the velocity they come off the ramp at. So it has both magnitude and direction, 30 degrees above the horizontal at 20 meters per second. Everybody with me there? Okay. So that projected velocity has both a horizontal, or x component, and a vertical, or y component. Agreed? When he comes off of that ramp, he's going somewhat up and somewhat forward. So we need to figure out how much up and how much forward, okay? So that we can start figuring out the 2 components, the vertical and horizontal components of this trip. Okay? So, first thing we're going to do is break this up into vertical and horizontal parts. Okay, right now, I do know one thing vertically. Gravity, exactly. His acceleration, at this time I'm going to make it negative, is negative 9.81 meters per second squared. The reason I'm making it negative is because he initially is moving upwards, okay? But at the end, he'll be moving downwards, all right? Okay, so we've got that. We don't have anything else yet, but we can figure some things out. If I find this side of his projected velocity, that will be his initial vertical velocity. How fast he was moving in an upwards direction at time 0, at the time of launch. Okay? So how would I find that side, or that y component? Right, I'd use sine. Okay? Just like we did back when we were doing vector addition. If I want to find the opposite side, I use the sine of the angle multiplied by the hypotenuse. Okay? This is why we learned how to do vector components. All right, so I'm going to find that side. It'll be my initial vertical velocity. So I'll go sine of 30 times 20 meters per second, and I'm going to find that he was moving upwards at 10 meters per second. That was his initial vertical velocity. Okay. If I find the horizontal component of this projected velocity, that will be his horizontal velocity. And that number won't change because we know horizontally there's nothing to speed him up or slow him down. He's traveling at a constant velocity in the horizontal plane. So how will I find this side of the triangle? Cos. Okay, so I'm going to go cos of 30 times 20 meters per second. All right, so we're looking at 17.321 meters per second. Okay. That's all I can calculate. The rest I have to figure out. Okay? And the one thing that I have to figure out right now is I need to know one more thing from a vertical perspective. Okay? Because I need to find the horizontal distance. Okay? I need to figure out where I've got to put that kiddie pool. Okay? And where I put that kiddie pool is along the horizontal plane. Okay? So I need to know the horizontal distance. But in order to get that, I need to know. Okay? I don't have that right now. Nor do I have enough information vertically to help me get it yet. Okay? Here's the other thing I need to know about any vertical movement. Okay? Watch carefully. Throw this marker up in the air. What's going to happen? Really? Okay. It's going to come back down. Okay, so I throw it back up in the air. All right, it comes right back down to my hand. Now, if I throw it from this level, it goes up and it starts slowing down immediately after it leaves my hand, right? Because now I'm not pushing it anymore. So it's slowing down, slowing down, slowing down. It gets to its maximum height where its speed would be 0, and then it starts accelerating back down, still at 9.81, right? Its acceleration both up and down is downwards at 9.81 meters per second squared. So it goes from some initial velocity to this maximum height where its speed is 0. Then it falls from 0 back down exactly the same distance at exactly the same rate of acceleration to exactly the same height that it came from. How fast is it going when it gets back? Before. The instant it hits my hand. The same it left at. Because everything is the same. Okay? It accelerated downwards on the way up and went to a certain height and reached a speed of 0. Then it fell from 0 at the same rate of acceleration for exactly the same distance, which means it comes back here at exactly the same speed it was thrown at. Okay? So in the perfect physical world, if you threw something upwards in the air, when it came back to you, it would be going exactly the same speed you threw it at. In the real world, that doesn't happen because objects tumble. Okay? And when they tumble, they actually slow down. Right? It's the reason why if you were on the ground and you shot a bullet straight up in the air, you wouldn't have to worry about dying when it came back down. Okay? Because when it comes back down, it's going to tumble. It's not going to be going fast enough to hurt you. Okay? I don't recommend you try that. Okay? But it's not something you really need to worry about a whole lot. Plus, there'd be wind, and it's very unlikely the bullet would actually fall straight back down. And if it did, it would go right back in the gun. But okay, you get the idea. All right. So, in this case, though, we're going to say we're operating in the perfect physical world, so the final velocity of this person vertically is going to be not positive 10, but negative 10. Okay? Same speed, different direction. All right. Now I have VI, VF, and A. Can I find time with those three things? Yeah. I can use my good old science 10 acceleration formula. Right? That's got those four things in it. All right, so I'm going to solve for time. Time's going to be negative 10 minus 10 over negative 9.81. So I'm just going to go 20 divided by 9.81 because that's what that's going to come up to. Okay. All right, so this thing is in the air, this person is in the air for 2.04 seconds. Okay, can that time go over there to the horizontal part? Yes, because the whole time they're up and down, they're also going side to side. Okay, so 2.04 seconds. Now, since I know how fast they were going, and I know how long they were going that fast for, I can figure out how far they would go. D equals V times T. Okay, so that'll be our 17.321. Okay, so we'll go multiplied by 17.321 32050808. Okay, I need to put the center of that pool 35 meters away. Okay, and that person will land in it, theoretically. Okay, so this is the type of calculation they would have to do. All right, so is there any new math here? Anything we haven't done before? No, it's all stuff we've already done in this unit. It's just being combined now into a different context. We can do acceleration problems. We can do v equals d over t problems. We can find vector components, x and y. Okay, all of those things are things we know how to do. Now we're just using them in a practical application. Okay? All right, so now we're going to see what Adam and Jamie did with this. Okay. So we got a ball that rolls off the table like so. Okay, it hits the floor 0.85 meters from the base. Okay, the table's 1.2 meters high. What speed did it roll off at? Okay, so that was one of the other things I said you might be asked to calculate for a horizontally projected projectile. So I want you guys to see if you can solve this. Okay, so as with all projectile motion problems, we want to separate this into our vertical and horizontal components. Vertically, I know my initial velocity is 0 meters per second because it says the ball rolled horizontally off the table. Okay, I also know that my acceleration is 9.81 meters per second squared downwards, and I know that the displacement is 1.2 meters also downwards. Horizontally, all I know right now is the horizontal distance traveled is 0.85 meters. Right? If I'm going to find out how fast the ball was moving horizontally, I need a time. Okay, can I find time with my vertical information? Okay, so it happens this way, guys, with most of your projectile motion problems. You're going to have to find enough information to get time, then you can apply time to the other side and solve the question. Okay, so in this case, we're going to use d equals vi times t plus 1/2 at squared, and we're going to solve for t. We can do that because vi was 0. Right, so t will equal the square root of 2 times d over a, or d over half of a, whichever will work out the same. Okay, so we're going to have the square root of 2.4, because that's 2 times 1.2, okay, divided by 9.8. All right, so we've got a time here of 0.49 seconds. Right, now I can take that number over here, because the whole time it's falling, it's also moving horizontally. V equals d over t, 0.85 divided by 0.49, right? And we'll get our horizontal rolling speed, okay, that the question asked us for. So 0.85 divided by our answer. All right, so it rolled off the table at 1.7 meters per second. Right, so these are very typical types of questions that you might get on a quiz or unit exam. Okay, I would expect that on your first unit exam, you could expect to see projected horizontally type of question, as well as a projected at an angle question. Now we haven't gone over, we've only gone over one of those, okay, and that was the mega whoosh one here, but we'll look at a few more, okay, as we go along. All right, so I'm going to show you a video clip here in just a second, okay, and it's from this old show from like the late 70s, early 80s called The Dukes of Hazzard, which was like one of the greatest shows ever. Okay, I mean by today's standards, they're not even allowed to show it, even though it was a fairly wholesome show. Okay, there's a lot of controversy around the fact that there's a Confederate flag on the top of the car. Right? And that's why they can't show it on TV anymore, because apparently that promotes violence. Yeah. Other things don't promote violence that are allowed, but that does. So we can't watch this, otherwise it's a wholesome show. But anyway, okay. So I'm going to show you a couple of video clips here. Basically, the whole premise of this show was this family of people in Georgia ran moonshine, which was illegal, and they got caught, and they were always trying to get away from the police in their area because the police were crooked. And they would, for some reason in this county, there were roads that went across rivers but didn't have bridges. So everybody just jumped over them, jumped over everything. Okay, apparently all cars in this county could just jump over things. Okay, crazy land, and yeah, it was cool. Okay, so I'm going to show you a bunch of the jumps that they actually did in the show. Now remember, this show was filmed in the late 70s, early 80s. This is pre-CG. There are no special effects to these jumps. People had to plan them. There was a driver in the car for all of them. It wasn't done by remote control. Okay, all of this stuff had to be planned out and then actually executed. Not like in today's thing where you just drive a car up to a ramp and then, okay, we'll CG the rest in post-production. Okay, these are all real jumps. You can see some of the things that actually kind of go wrong sometimes in some of these jumps, because sometimes they don't cut away quickly enough. The only special effect they would have is they would jump the car, show the car flying through the air, and then just before it hits the ground, or sometimes just after, they cut away, and they have a scene where the car, a different car, is driving away from the landing point. Okay, because the car that actually did the jump is destroyed. Okay, now the General Lee is a '69 Dodge Charger, one of the most beautiful cars ever built. They destroyed hundreds of them in this show. Okay, literally hundreds of them. By the end of this show's run, they were having to jump different types of Dodge cars and film them from different angles because they couldn't find chargers to destroy anymore. Okay, they couldn't straighten the frames on the ones they had already wrecked. Okay, so I'll show you some of the videos, and you guys can. There's one particular jump that this question relates to. Okay, so we have the General Lee jumping over the riverbed. If you don't have this question written down, write it down. This will be your first example of exactly the kind of thing I would ask on a test. Okay, the following information is known. The speed of the General Lee is 32 meters per second, around 125 kilometers an hour. Okay, when it leaves the ramp. Okay, the ramp is angled at 20 degrees. We're looking for the distance across the river and how high above the riverbed the General Lee ends up at its maximum height. Okay, so we're looking for two things here. So this is what we have. We know that the launching velocity is 32 meters per second, angled 20 degrees above the horizontal. Okay? We know the General Lee follows a projectile arc path that re-encounters the ground on the other side of the river. Okay? So I want to calculate how far this is. So that's a horizontal distance. So I want to calculate the horizontal distance, okay? And I also want to calculate the maximum height, which would be a vertical piece of information. Okay, so the maximum vertical displacement would be what we're looking for. Because over the whole trip, what's the vertical displacement? Zero. Yeah. Jumps off the ramp, comes back down to the ground. Overall vertical displacement is zero over the whole trip. Okay, what we're looking for is what's the vertical displacement right here? Okay, the maximum height of the General Lee. That's the second thing we're looking for. Okay, so in order to figure this out, we've got to calculate the horizontal and vertical components of this projected or launched velocity that we have. Okay, this side of the triangle will represent our initial vertical velocity. This side will represent our constant horizontal velocity. Okay, because they're the vertical and horizontal components of the launched velocity of the General Lee. Okay, everybody with me so far? So how am I going to calculate VI? Sine. All right, so I'm going to go sine of 20 times 32. Okay, so initially, the General Lee is being launched at 10.94 meters per second in an upward direction. Okay, now, since it goes up and comes back down to the same height, how fast is it going vertically when it comes back down? Negative 10.94. Remember when I threw the marker up earlier in class? Okay, same situation. Negative 10.94 meters per second. This becomes a bit more complex if those two heights aren't the same. Okay, it adds kind of a third part into the question. Basically, it ends up being like something thrown off a cliff added on to the end of this question. Okay, we're not there yet. All right, so we've got that information there. We also know the acceleration is negative 9.81 meters per second squared. What can I calculate right now with that information? Time. And I should probably do that, because we know time can apply to both vertical and horizontal. Okay, so we're going to go for time, sorry. We're going to go VF minus VI over A. Okay, so that'll be negative 10.94 minus 10.94 divided by negative 9.81. Right, so I'm just going to take that number, multiply it by 2, and then divide by 9.81. All right, so the general E is in the air for 2.23 seconds. All right, so that's a number that I can now transfer over here. Okay, looking here again at my vertical information, one of the things I'm being asked to find is the maximum height of the general E. How fast, vertically speaking, is the general E going here at its maximum height?
Like 16 meters or something.
Nope. Watch the marker again. Tell me how fast the marker's going at its maximum height. 0. Okay? I'm not saying that the general E isn't moving. It is. It's moving horizontally, probably at 16 meters per second. Okay? No, probably faster. But it's going fast horizontally. But from a vertical perspective, if all I can see is the general E from a vertical perspective, all I see is a car going up and down. Okay? That's it. And at its maximum height, its speed is 0. Okay, so here, VF equals 0 meters per second. That's just something I have to remember or understand about all projectile motion. At the maximum height, that's the point of turnaround. Okay, so if I know VF is 0 there, I know VI is 10.94, and I know the acceleration is negative 9.81. Can I solve for D? Yeah, I can use this formula. Right? That has the 3 pieces of information that I have. VF is 0, VI is 10.94, and A is 9.81. Okay, so I just solve for D. So I'll have VF squared minus VI squared over 2A equals D. Okay, so that'll be 0 squared minus 10.94 squared divided by 2 times negative 9.81. That way I get a negative on the top and a negative on the bottom. Okay, and I'll get a positive displacement. So I'm going to take my 10.94 squared, and I'm going to divide that by 19.62. That's 2 times 9.81 in case you're wondering what I'm shortcutting there. Okay, so the general E reaches a maximum height of 6.1 meters. That's roughly the same as dropping it off the top of the gym. Okay. That wouldn't be good for to be dropped from that height. Do a lot of damage. Not to mention what it would do to the people inside. Okay? Yeah, being a stuntman for this show was a hard line of work. Okay? Most of those guys had like thumbs they couldn't move anymore. Okay? Incidentally, if you ever become a stunt driver and you jump a car, hold on to the steering wheel like this. Thumb on top. Don't put your thumb around the steering wheel. What will happen when you hit the ground? Snap. Yeah. Break your thumbs, break backwards. Okay. You can always tell a stunt driver they hold the steering wheel a certain way. Okay. So 6.1 meters, okay, is our maximum height there. All right, so that was one of the 2 things I was asked to find. The other thing was, how far was it across the riverbed? Well, I have the time. Can I find how fast it's going horizontally? Right, well, I can go back to here, right? This side here was supposed to be our horizontal velocity. So what trig function do I use for that? Cos. So I'm going to go cos of 20 times 32, and that'll tell me how fast it's going horizontally. Okay, so it's moving at 30.07 meters per second horizontally, and it's going to do that for 2.23 seconds. I'm putting in the whole number there. Yeah. Okay, so the general E flies 67 meters horizontally. To give you some idea, that's 2/3 the length of a football field. Okay, so it means it jumps from one end zone to basically the 30-yard line of the opposite side of the field. Pretty far. Okay. Alright. I had that as the unit exam question 2 semesters ago on the unit exam. That is exactly the type of thing I might ask on a unit exam. Probably not that exact question, because obviously I just told you, but it'll be something like that, I'm sure. Okay. All right, questions on how that one works? Okay. Write that one down and give it a try. Basically the same question, except instead of the generally, it's cannonball. Right? See if you can remember what we did. Okay, see if you can repeat it.